we're very happy to have Jan de Boer from Amsterdam talking about semi-classical gravity, statistical physics. So, please go ahead.
All right. Thanks for the invitation. It's always a great pleasure to be in Paris. The title of this talk is Semi-Classical Gravity Equals Statistical Physics. And the main point I want to make that is quite literally something that seems to be true. And I'll try to explain mostly what that sentence means in the remainder. So this is based on a bunch of work from that started roughly 2.5 years ago. Most of it with Alex Bellin, also with my student Diego Lisca, with Julian and the postdoc Pranjal, etc. And one paper was also with Tarek and Noes. I should also advertise that Diego will be giving a talk here in a couple of weeks, and that will be, I think it's called Polytechnique. And he will speak about some things that I will say very little about, so that will be mostly complementary to what I'm saying here. So if you want to hear more about this type of stuff, you should go to that seminar as well. Oh God, it's, yeah. No,
okay,
yeah, here we go. Yeah. After 3 years of COVID, so we're slowly figuring out this technology stuff. So the main question that drove sort of this program was the question. It's mostly an ADS-CFT, although it's interesting to think about the same question in other contexts as well. But the most important question, in some sense, is if we do ADS-CFT, and we restrict ourselves to semi-classical gravity in ADS. So we're not doing full non-perturbative string theory. We're just doing semi-classical gravity in ADS. What features and what parts of the CFT are uncovered by that? And what kind of description in the CFT is exactly equal to semi-classical gravity? So which pieces and parts of the CFT can one see and which parts and pieces one cannot? And you might naively think that since you're doing low energy effective field theory in ADS, that is going to be the same as doing low energy effective field theory on the boundary. But it's a really peculiar feature of gravitational theories that is more interesting than that. So a low energy effective field theory of gravity is not just a low energy effective field theory approximation to the CFT on the boundary. It is something more complicated. And one reason why it's a bit more complicated is that gravitational theories, even if you just do semi-classical gravity, it knows more than just low energy physics. For example, in ADS-CFT again, if you put a black hole in ADS, you can compute the entropy of the black hole. You can do that for an arbitrarily large black hole in ADS. And in that way, you can basically find out what the partition function of the CFT is, even at very high temperature. To compute the approximate partition function at very high temperature, you don't need any non-semi-classical physics. All you need to do is sort of put a large black hole in ADS and compute this partition function semi-classically. You can look at many other partition functions because you can take other boundaries in ADS and compute partition functions on those manifolds as well. That has more, again, same spirit as that. In particular, this includes all kinds of sort of high energy information because you can make cycles on these boundary manifolds as large and as small as you want. You just need to make sure that the semi-classical approximation is good. But if it is, then you get a lot of additional information in that way. And although I'm not going to talk about this, it's also interesting that you can even get the so-called phase curve for black hole evaporation out of a semi-classical computation, although this requires a few more ingredients than just semi-classical gravity. Because it's not really clear. There is a well-defined notion of the phase curve if you only do semi-classical gravity. But I won't be speaking about that. Then there's another interesting feature of semi-classical gravitational theories, which is maybe puzzling, and that is that semi-classical gravitational theories seems to give rise to correlations between theories that shouldn't be there. The standard cartoon is this Euclidean wormhole solution. Many semi-classical gravitational theories with a very large footnote, have wormhole solutions that roughly look like this. And those wormhole solutions, naively, so these are Euclidean wormholes, they're not Lorentzian wormholes, they're Euclidean wormholes. They naively give rise to some correlation between the two boundaries. Those correlations between boundaries are very strange because naively they seem to tell you that the boundary theory is not a single CFT, but it is maybe something like a disorder average over CFTs or something else. So some extra thing has to be there that creates the correlations between the two boundaries. But we take these solutions seriously. And that we always thought ADS CFT that like ADS was dual to a single CFT. And if ADS is dual to a single CFT, then these correlations should be absent. In particular, this picture, naively, it contributes to a computation where you compute the partition function of one CFT on this boundary times the partition function of a second CFT on this boundary. And it's a geometry that contributes to that computation according to standard ADS CFT. Because standard ADS CFT tells you, well, you just write down the boundary geometry. In this case, the boundary geometry is two disconnected circles times some spatial manifold that I didn't draw. And there will be two disconnected solutions. That will be the dominant solution. That will just be the product of two leading order partition functions. But then there's these kind of weird sub-leading wormholes that seem to correlate the two theories on the boundaries. This is sometimes referred to as the factorization puzzle. So if these solutions exist in a semi-classical theory, what's their interpretation? Does it imply that at a fundamental level, gravity cannot be dual to a single unitary theory, but should somehow involve an average over theories? Because that's the standard way in which we know how to create correlations between two boundaries. Or is there something else going on? Yeah?
Are they always sub-leading?
Yeah, I don't think we know any example where there exists a wormhole which is the leading contribution to something.
Yes, there is. The two sides are ADS, the two boundaries are ADS. Typically, there is no solution that has only one boundary.
If you put the theories on ADS boundaries.
Then if you want to model like some
okay, good. Yeah, I need to think about those examples.
Like that, I wanted to ask precisely this question.
Yeah, no, that's a good point. Yeah.
But I think it's still true, as Jan was saying, if you take the boundaries to be closed manifolds, then probably it's always experimentally the dominant solution is always this
Yeah.
way. But I'm not sure.
No, because even in this case, take ADS and you mod it out by some discrete root to make it compact. The geometry doesn't change. It's still...
But then you have to convince me that that's the dominant solution. Whereas there are other solutions.
Well,
And if you have not
I don't know
yet,
any. Yeah, okay, I haven't convinced.
Yeah. But it's possible that in those cases, the disconnected solution might involve some mild singularity, which is resolvable in string theory. And then the question becomes whether you think those are reasonable things to include in your semi-classical theory or not. So this word semi-classical theory can be defined in different ways. If those mild singularities are of this sort of okay type, then you could agree that these should be part of what you call a semi-classical theory. Yeah. So with that extra statement, I don't think there's any obvious example where the wormhole dominates. It would be very interesting to find like a clean example with two compact boundaries where it really dominates. So that would sort of put the puzzle in the sharpest possible perspective. Like if the boundary is like a Euclidean ADS or even some quotient of that, we do believe the partition function of the theory with a single boundary exists in ADS CFT, right? It's just one. Yeah. So then, if the both solution has a mild singularity, it's presumably in the good category of singularities and should be resolvable somehow. But then, then it's up to you whether you decide to include that in what you call the semi-classical theory or not. Yeah, that's in general an issue with any theory above 2 dimensions that you put on a negative inverse space, that the scalar couplings will destabilize the theory. So that's another issue if you put the boundary on ADS. Absolutely. Now there's a special case where these wormholes exist and where you can completely stop the theory, which is JT gravity. It's a 2-dimensional topological theory. That's a somewhat misleading and atypical example in the sense that that's a simple topological theory that is kind of UV complete, so you can just solve it. You don't need to UV complete it using string theory or anything. So it's not really a standard example of ADS-CFT. It's really a different type of example. It's a topological theory. You can solve it. And you can, in that particular case, you can see that it's dual to some matrix model. Now, a matrix model is an integral over theories. Like each matrix, you can sort of think of as being a Hamiltonian of theory. So a matrix model is like an integral over theories. You could even think of it maybe as like a very large disorder theory, where like all these matrices correspond to sort of different disorder parameters in the theory. And it's clear that if you have a matrix model, you will have these correlations. Because you can just take 2 boundaries in your matrix integral. So if you compute trace E minus beta 1m times trace E minus beta 2m, and you do an integral over m, with some e to the minus trace, some potential of m, clearly this thing will have a connected 2-point function. So there's no surprise in that case that these wormholes are really meaningful. They just give you the correlations in the matrix model. But this is a very atypical and maybe somewhat misleading example. Because clearly this is not how gravity is supposed to work in high dimensions, where you have dynamical gravitons and we allegedly need string theory to UV complete theory and so on.
Also, if I remember correctly, you mentioned that yes, it's disconnected boundary already. Boundary with yes is.
Oh, if you do it like that, yeah, but there's also solutions with one boundary, yeah.
I mean, already in the standard like vanilla case, you can have.
No, it's very easy to make 2 boundary. It's a very simple theory, and but you do have one boundary solutions, like just the disk. The hyperbolic disk is also a solution for a Euclidean ADS2. So that's the simple solution. It's just a hyperbolic disk.
The fact that this can arise as a reduction of high-dimensional gravity is not.
It's a sector of high-dimensional gravity. So you could argue that if you're not semi-classical, but much worse than semi-classical, and you sort of Kaluza-Klein reduce all the way down to 2 dimensions, and you ignore everything else, if that's your definition of semi-classical gravity, then you might end up in this particular corner. But it's a very peculiar. You basically threw away almost everything. And if you're an observer like that, then maybe this would be your dual description. Because yeah, that sector is captured by this matrix model. But that's not.
I would say that the averaging is induced somehow by integrating out the Kaluza-Klein.
I'm just saying that this is the best description of those computations in that sector. But we'll get back to that. I think this point will become clearer later, because I don't think you really doing this Kaluza-Klein reduction. I don't think you should think of it as averaging per se. But we'll get back to that. But it's very different because this is an exactly solvable model. You can compute a partition function of the JT theory. But in high dimensional examples, if you do a semi-classical computation, you just get some approximate answers to something. You never get an exact answer unless you do BPS things and you can, do localization or something. But if you do generic computations, you just get some approximation, some leading large Armstrong coupled approximation to anything. And what these computations give you is not something averaged or anything. It gives you something coarse-grained. That is how we normally think about that. Now, these words, averaging and coarse-graining, are kind of close to each other, but they're subtly different. So coarse-graining roughly means the following. Suppose that you compute the entropy of a black hole in ADS-CFT. So we compute a partition function in some approximation. We never compute it exactly, it's in some approximation. Then we know we can write that partition function as the integral of a spectral density times some Boltzmann factor. And in an exact computation, if you would do the inverse Laplace transform of this thing, you would get a sum of delta functions, because we know that this is the actual spectrum of the theory in ADS-CFT. It's a discrete spectrum. However, if you do this gravitational computation and you extract the spectral density from it, you do not get a sum of delta functions, you get a smooth function as a function of energy. We normally think of that as a coarse-grained version of the sum of delta functions. And that has to do with the fact that we made an approximation, and that approximation that we make by doing a semi-classical computation involves some sort of coarse grading. In other words, we have smoothed out the sum of delta functions somehow. If you wanted to technically do it, you could maybe integrate this against some sort of Gaussian and use that as some sort of filter for the coarse graining. There might be different ways to do it, but that's normally how we do it. So it's clear already from these symbols examples that although we get some information about the high energy sector of the theory by looking at black hole partition functions, that energy is coarse grained. It's not exact UV information, it's coarse grained UV information. Now, coarse graining and averaging are not exactly the same thing, but they are very similar to each other because both blur out some information. If you do like an integral over some, if you have a Hamiltonian that, for example, depends on the disorder parameter, and you integrate over some disorder parameter, and you look at the spectrum of the theory, you also blur out the spectrum. Coarse graining also blurs out the spectrum. So averaging over a disorder parameter and coarse graining superficially look very similar to each other. And therefore it's tempting to think that in higher dimensional ADS-CFT examples, where gravitational computations do some sort of coarse graining, it is that coarse graining that is responsible sort of for the appearance of these wormhole solutions. And it's this coarse graining which sort of generates fake correlations in the system rather than averaging. And again, these two things are subtly different, but it's important to emphasize that coarse graining applies to a single theory. And in principle, by increasing the precision, doing more and more precise computations, you would see that as you increase the precision, that the coarse graining becomes more and more narrow. And in principle, in the limit of infinite precision, one should recover a single CFT. Whereas if you do some disorder averaging, even if you increase the precision, you will always be left with some finite width of coarse graining that is set by the scale of your disorder average. So that's the subtle difference between the two. Yes.
So when you average, when you have, for example, some random CFT which doesn't have a scale separated spectrum over the kind which is due to gravity, if you take a bunch of them and you average over them, in principle you can wipe out all the states in between, and you end up with a theory which has some nice low lying modes, and then has some high dimensional operators which is due to gravity. But so just wondering what the averaging, coarse graining can never do that. In coarse graining, when you have a theory which has some spectrum, which doesn't have any separation of dimensions, you can average as much, you can coarse grain as much as you want. You'll never get a still separated spectrum. While by averaging, for example, if you get some theories which again have continuous spectra, you can get them to, you can decouple. I mean, you can wipe out the states in the middle in the averaging, and you can get the theory which has a gravity fluid. So the question is, whether they have some theories which don't want to have a gravity fluid, and averaging is just a way to force them to get rid of the states of the.
Yeah, no, that's something that you can do, but that involves. That averaging involves a fairly brutal, that already has a big impact at low energies because you erase some states on the spectrum. Mm-hmm. So that means that the sort of the scale of that theory is very low. So for example, if you take like a CFT with some like Narayan moduli space and you average over the Narayan moduli space, you get something that is described by the Chern-Simons theory, some topological theory. Mm-hmm. But that's really basically only the topological sector of the theory is left because you erased everything else. But then you discover that this thing is not UV complete already if you go epsilon away from the topological sector. So yeah, you would quickly run into issues if you do such a drastic averaging. That's right.
But when you average to get the GT gravity, this is not averaging which is done. I mean, I'm just wondering whether the averaging would be good to get.
That's not really the averaging that's being done in GT. No.
In GT, it's like everything's a heavy state.
Yeah,
There's no,
it's
light stuff, all in the black.
it's a bit like getting rid of everything below the black hole threshold in the 2D CFT and sort of averaging from the black hole threshold onwards, something like that. Cool. Now, just to give you an idea of how a semi-classical gravitational theory, if you coarse grain, how you might make how that can give rise to an apparent inconsistency in a computation if you coarse grain. So this is a very simple cartoon mistake that you might make if you coarse grain computations. So suppose I take a bunch of faces that I draw from a random uniform distribution. It's a large number of faces, let's call it n. So I write the sum of a bunch of erratic faces. If you coarse grain that, then the best guess is 0. Because what else could it be after coarse graining? It's just a bunch of faces. And if you multiply it by the complex conjugate, again, if you coarse grain this, you get 0. It's just a bunch of random faces. If you multiply it out, then you have a diagonal term and an off-diagonal term. You could argue that the off-diagonal term is again a bunch of random faces and coarse grains to 0. What else could it be? But then the diagonal term is a bunch of 1s. If you coarse grain that, there is nothing much happening. So this is something that could survive coarse graining and give rise to an n. So if you do coarse graining in this way, you're left to some sort of apparent contradiction that 0 times 0 is n plus 0. And you could think that this n is somehow is the wormhole. Because this is kind of if you think of this as the theory on one boundary, and this is the theory on the other boundary, this is kind of the correlations, the fake correlations between the two systems. Mind you, there's no correlation whatsoever here. I took fixed random faces. I'm not doing statistics. I just sampled a bunch of faces, a large number of them. So you see that coarse graining can make mistakes. And perhaps these wormholes, they're just a result of a coarse graining procedure, and they give rise to an apparent contradiction of something. But it's not a fundamental contradiction. It's just an apparent mistake that you make, and it arose due to coarse graining.
Is there anything about the fact that the 0 is the 0 of the n squared term?
Yeah, of course. This knows that the average variance in this thing is n. That's what that is signaling. However, this thing does not have a well-defined. You just know how large the average fluctuation is, but you don't know the actual value. So if you were to coarse grain this, you would have to pick a random direction with some amplitude, and that random direction, there's no preferred choice. So that's why this cannot be coarse grained to anything reasonable. So you could say the wormhole knows about the average fluctuation in this guy, but not the actual value. There's no sensible coarse grained answer to it. So that means this is roughly the cartoon. Now suppose that this is the right cartoon intuition for what coarse graining does and why it gives apparent mistakes that are captured by type of wormhole type things. Then you can ask what happens in the full UV theory. Because ultimately, once we increase precision and we add more and more UV ingredients, we increase the scale of the theory. You increase the precision of the theory, etc. At some point, one might think that if you think AES CFT exists and that there is a duality with like a single CFT, one should eventually recover the full UV and see that this is just a product of numbers. Now, there are a couple of logical possibilities for what could happen. So one possibility is that as you add more and more UV ingredients to the theory, that eventually this wormhole gets destabilized and is no longer a saddle point that should be included in any semi-classical evaluation of the path integral. The second possibility is that somehow there are many, many new complicated fluctuating solutions in the gravitational theory that somehow add all these weird fluctuating terms in such a way that it precisely adds up to something factorized. That's also logically possible. Yeah, and the third possibility is that you will never restore factorization, but then the conclusion would be that you're in doing some sort of averaging. Because if you don't restore factorization in the UV, then clearly there's some fundamental averaging going on. So these are the three possibilities, and I think currently it's not exactly clear which of those possibilities is exactly happening. Although we have no example at all of the second scenario. So I think as far as we know, it's the first scenario that applies. But it would be nice to understand that better. You might think that there should be a universal, somewhat universal way in which the theory restores factorization. And this seems to be a very complicated way to restore factorization. This seems to be a simple way to restore factorization. And there might be some nice and simple understanding of what should happen in general. A very rough, simple argument for the first point could be that if you have typically wormholes, they're a bit like ADS solutions, so they're supported by fluxes. Now, if you have fluxes, then there will be objects that are charged under the flux. And in particular, those objects could possibly be nucleated in the wormhole by some, again, stringer pair production type mechanism. And if you nucleate enough of those, they will back react and they can sort of break up the throat. And maybe there's like a swampland type argument that this must happen somehow. And maybe it's even a version of this cobordism conjecture that can be used to argue for this. I'm not quite sure, but that seems not an implausible scenario. It would be nice to put that on a firmer footing. Yes.
Sorry. So what is the exact difference between the first two? Is the first one that factorization is restored in the low energy area, while the second one is that factorization is restored in the UV?
Well, the first one, in the second case, this thing would remain as a saddle point, even at higher energies, as a reliable saddle point. In the first case, it would not. So it's really the quality. So if this thing remains as a bona fide saddle point, even in the UV, if you wish, then other things must come in that cancel it and that restore factorization. But if it gets destabilized as a saddle point, then we no longer include this if we do a semi-classical computation. And then this issue, as it stands, is not right.
From the boundary theory point of view, there's no difference. Boundary theory doesn't know what's the saddle point.
The boundary theory couldn't care less. No, it does not know about either of those two things. As long as factorization is okay, then yeah.
The cartoon kind of favors the second.
Yeah.
Sorry? Your example at the top kind of favors the second solution.
Well,
I mean, that's what happens in this.
That example favors the second one. That's right. But I don't think this is realized in any known gravitational setting. Yeah. There are these nice things like there is some suggestions for the second one have to do with this thing called the Woods-Wilder trace formula, which sort of relates exact partition functions to periodic orbits in the classical system and sums over those. And you might perhaps believe that this has some relation with all those periodic orbits, that if you're able to really solve the field equations more accurately, you might find all those periodic orbits, and then that's how somehow the whole thing gets restored. But I don't think this has been accurately achieved in any example.
In the first scenario, is it important to you that to distinguish between perturbative and non-perturbative instability?
In principle, not, as long as it gets destabilized one way or the other. Perturbative instabilities would just kick in earlier. The problem with perturbative instabilities is that maybe by deforming the contour through complex metrics or something and complex field values, maybe by deforming the contour you could still sort of make sense of that as a saddle point in some complexified set of geometries. And I don't think we fully understand the rules of which contours we should choose in all cases. So in the case you have the conformal factor to deal with already anyway. So that's it's a bit harder to figure out when those things are really problematic and when not. But yeah.
At some point, we'll talk about ideas 3, I guess.
At some point, yeah. Yeah. And this is the a silly cartoon that you all know of what happens to the spectrum of a field theory as you increase from weak to strong coupling. At weak coupling, there's some regularly spaced spectrum, and a strong coupling, you get a sparse spectrum of light states and a very dense spectrum of heavy states. This is where black holes live. Here, the level spacing is believed to be E minus S. This is believed to be chaotic. This sector is roughly the interval sector of the theory. And the main claim is that semi-classical gravity is a theory that has some knowledge of this chaotic. It has some knowledge of this chaotic sector, but only statistical knowledge. So it knows about sort of the statistics of all these things, but it doesn't know individual values. So it can prompt all kinds of statistical features of the high energy spectrum, but not the individual values. And in particular, it cannot distinguish sort of average from coarse-grained answers as long as the averaging is small enough. And as long as the averaging is so small that it is sort of within the error bar of your low energy computation, because then you will never be able to detect it with the accuracy that you have available. So this is kind of interesting, and you may ask whether this is some sort of fundamental limitation on if you're an observer in the system and the system has a very complicated high energy chaotic spectrum, whether there's some fundamental limitations on how much information is fundamentally obtainable to you as a low energy observer. Now, in order to make more precise what we mean by a theory of the statistics of the chaotic sector, I'm going to use standard statistical physics principles as follows. And a nice way to think about statistical physics is that it's like a maximal ignorance principle. And the simplest example to illustrate that principle is to derive the canonical partition function of a theory from this principle, which goes as follows. You simply write down the entropy of some density matrix minus trace rho log rho. That is quantifying the uncertainty, right? That's the entropy. And now we maximize the uncertainty subject to one condition, namely that the expectation value of the Hamiltonian is a given energy input. And that we enforce with the Lagrange multiplier. If you do this, you maximize uncertainty with one input, namely that the energy is fixed. You maximize this functional for rho, then you find precisely that you get the canonical ensemble to come out. This is a very straightforward way to get the canonical ensemble. But we want to sort of apply the same thinking, but not to just this, but to semi-classical gravity. Because in some sense, semi-classical gravity gives us some approximate input of a very complicated theory that is chaotic at high energies. We do not fully understand what it is, but we have some information about it. And so we are going to build a model of the theory that is the best possible description with maximal entropy subject to suitable low energy observations. So our low energy measurements, our low energy observations will be input, and the output will be some sort of statistical model in this period. To give you an example, another example of this thinking is that suppose that we have some operator A, and suppose it has 0 finite temperature 1-point function, and it has some non-trivial finite temperature 2-point function. Then you can ask, so the only thing I know is the finite temperature 2-point function of this operator. I don't know everything, I just know the finite temperature 2-point function. Then you can ask, what's my best possible description of the matrix elements of that operator, given the fact that all that I know is the finite temperature 2-point function. So I'm going to try to write some sort of statistical model for these matrix elements, subject to the condition that the finite temperature 2-point function is fixed to something. That's a bit more complicated, but I'm going to do exactly what I did before, but in a slightly more complicated way. So here's all these variables Aij, these matrix elements. Mu of Aij is some probability measure on these spaces of density of matrix elements. And this is the the entropy associated to this probability distribution. This is classical, this is not quantum. So maybe it should be called Shannon entropy. Or it's literally Shannon entropy. But this is a classical version of entropy. And then we simply have an infinite family of Lagrange multipliers here that multiply the constraint that the finite temperature 2-point function is some input function f that we have measured somehow. If you do this and you optimize for this probability distribution, you get a quadratic matrix model with some coefficients for these aij's. So the best possible description of these matrix elements is not that they have particular values, but the best possible description is in terms of a quadratic matrix model. That's a well-known quadratic matrix model because that's ETH. The so-called eigenstate normalization hypothesis, so let's ignore the diagonal term here, is the statement that matrix elements of simple operators can, for the purpose of simple computations, be approximated by some prefactors times the random matrix. This level is roughly a Gaussian random matrix. And so this prescription, this ETH, is the obvious thing to write down if the only information that you have available is the 2-point function of the operator, the finite temperature, and you apply statistical mechanics, then the best possible description of the system with that limited information is literally this eigenstate normalization hypothesis. So that's one way to think about ETH. It's again statistical physics applied to simple correlator.
You include the information about the entropy.
Yeah, that's also input, because you have to input some knowledge of the spectrum in order to do this more precisely. So that's kind of input, but that's again, that's also why it shows up here in this way. That's right. So ETH, it's a statistical statement. We're not claiming that this is an exact statement. It is just the best possible description of the system given limited inputs. But these are precisely also the types of inputs that are available in ADS-CFT. If you have an ADS-CFT, you can take a simple operator, you can put two simple operators on a boundary torus or on SD minus 1 times S1, and you can compute the finite temperature 2-point function using a semi-classical approximation. It just involves a propagator in a Euclidean black hole background. So this information is precisely available in ADS-CFT.
In principle, you have much more.
Sorry?
In principle, you have much more. You can go to P points.
Oh yeah, you can go to P points. Yeah, I'll mumble something about higher points in a second. This is just at the level of the quadratic theory. Right. And then the third simple example is a bit simpler. Suppose that.
But the point here is that gravity computed the entropy for you, but not an input.
Oh no, the gravity. Oh yeah, that's right. Well,
how does it do that?
From the black hole partition function. Yeah.
No, but how does it know the correct line? I don't understand. In your analogy here, you were using this S as an input, takes the distribution. But the point is that gravity is not just giving you fluctuations, given the entropy, it's also giving you the entropy.
Oh yeah, so I should. So the more precise statement was that. So this is, if you want to do this more precisely, these are the inputs that you need. And both inputs are things that you obtain from a gravitational computation. The first one you get from a black hole partition function, and the second one from a finite temperature 2-point function.
Yeah, I thought your goal was also to explain how gravity knows about that. This is information that we compute semi-classically. We're just trying to see what the best possible description of that information in the CFT is.
The 2-point function information is entering in the G of A.
Yeah. That's some sort of Fourier transform, essentially, that 2-point function information. And then the third example of this philosophy is that suppose that you have the partition function of a theory, C of beta. Suppose you know that, and you want to write a model for the theory, then you can write, try to model the Hamilton, like a probability distribution on the space of Hamiltonians. In such a way, again, there's an infinite number of Lagrange multipliers that enforce that the partition function is equal to the thing that you put in. And you can optimize this functional. This is easy to see. You get some sort of exponent of something complicated. But lambda of beta was just a bunch of Lagrange multipliers. It's some a priori unknown function that you have to fix afterwards by making sure that this condition applies. But what roughly stands here is a generic single trace function of H. Because lambda of beta can be anything. This is in some sense the genre transform representation of some function of H. So given some z of beta, the description of the theory is always in terms of a matrix model for the Hamiltonian. And a single trace matrix model. Now, it's amusing that regardless of the details of the theory, you can use this model. This is just the input. So the input is just partition functions, nothing else. If you input partition functions, then you get a prediction for a two-point function based on this model that we just wrote down. So this is now an output, and it's a consequence of lack of knowledge. If I knew exact Hamiltonian, there would not be such a connected thing. But I don't know the exact Hamiltonian. The only thing I know is these partition functions. I don't know what the actual Hamiltonian is. And that's why my best description of the theory with that information is a statistical description. That statistical description, because it's statistical, has correlations in it, and those correlations can be computed. And for this particular matrix model, it turns out that, for example, there is a very simple leading correction, which is sort of the leading connected two-point function of two partition functions, that doesn't depend much on the details of the theory. It's a very universal matrix model result that has to do more with level repulsion and so on, but it doesn't even depend on Z. It's kind of a universal thing. So you could say that just, you know, if you're a semi-classical observer and you do all these computations in a single theory, then this would be the prediction for some correlation in the system. That's just something that comes out from your lack of knowledge.
If you know how to do this averaging over a product, right? You're saying that the statistics of the first partition function and statistics of the second partition function, you have to find some mechanism to connect them. And
that mechanism goes to this statistical physics principle, which tells you that if you maximize the entropy of the system, that's the principle that gives you those correlations.
But if you tell statistical physicists that two disconnected systems are somehow correlated, they would still be surprised. Right? You're doing something else. You're introducing the notion of an angular bracket and then correlating the statistics.
That's right. That's right. So this is
There's some ensemble.
This is ensemble thinking, but this is quantifying the fluctuation in the uncertainty in a single Z, if you want. So you can also think of this as quantifying the variance in a single Z. And that's the variance that is intrinsic in your statistical description. So if I make, that's another way to think about it. Yeah.
Some kind of entropy of mixing technical.
Yeah, maybe some interpretation like that. Yeah, I'm not quite sure. Yeah. Now the rough structure you always get is that if your inputs are some functions of operators, and say they are polynomials of some order, then the output is always something that is a bit reminiscent of a matrix model with the same order. So if this is like a k-order polynomial, you get a k-order matrix model just by the same principle. And you can also apply this example, you can apply this thinking to, say, OPE coefficients in a chaotic CFT. And so the OPE coefficients of a theory are interesting objects in any CFT because they determine many of the properties of a CFT. It's important to distinguish light and heavy operators. So light operators are simple operators. They are not in the chaotic part, but in the integral part of the theory. And heavy operators, H, are in the chaotic part, so they correspond to black hole states. They have an energy which is above the black hole threshold. And then these OPE coefficients, they're not directly computable semi-classically, because semi-classically, so this would be the 3-point function of two light and one heavy operator. But semi-classically, we don't have these heavy operators at our disposal. So we cannot compute these things directly, but you can compute averages of these things. So for example, if you compute the 4-point correlator for light operators in the right kinematic regime, the intermediate channel is dominated by heavy operators, and then this 4-point computation will give you this, but it's averaged over H. Some sum over H. There's lots of other things in conformal blocks, but this is the rough structure for this 4-point function. So this is information that's available, but not the individual values. Similarly, by looking at two light operators, say on a torus or in higher dimensions of finite temperature, it gives rise to these types of sums and such types of diagrams, which in a 2D CFT would correspond roughly to a genus 2 partition function, because there's two loops. They correspond to these types of sums. So if you compute genus 2 partition functions, 2-point functions in genus 1 and 4-point functions at genus 0 in 2D CFT speak, these are all semi-classically computable in ADS-CFT. So all this information is semi-classically available.
Sorry, what is the 4-point function? I mean, if I think about Witten diagrams that
no, this is the boundary. So in the boundary, if you go to a particular kinematic regime, right? So So based on the limit where on the boundary these points have a large separation, and then you have the operators. So that will be important. If they get very close, identity dominates. If it's far away,
so some kind of late time.
Well, it's just some feature of the cross ratio. Yeah. The bulk is interesting. So if this is dominated by heavy operators, then typically the cross channel is dominated by the identity operator. And gravity knows that because gravity has large difference. And so gravity will take out the simple Witten diagram. And it doesn't have to. So on the gravitational side, we never need heavy operators at all because gravity is smart enough to do this computation slightly differently. It automatically selects the simple channel, if you wish, and that gives the right answer. Gravity knows about crossing.
Is there a German rule for the statistical model before you extremize it?
The statistical model before you optimize the entity?
That's some way to think about the UV.
Yeah, it's a great question. I don't know. Nothing comes to mind, but yeah, it's a nice question. So, just by applying the same logic, we then end up with what's called the what we call the OPE randomness hypothesis, which is just a version of ETH, the eigenstate normalization hypothesis, and it applies to random OPE coefficients. To OPE coefficients with heavy indices, and since all our inputs at this level were quadratic indices, the result is some sort of quadratic matrix model-like entity. Except that for this, it's more like a vector model. This is more like a matrix model. This is more like a tensor model. But it will just be quadratic. That's why there's approximately Gaussian random variables appearing here. It just follows again from this principle. So if you build a statistical model of the theory with this logic, you automatically get into this operator randomness hypothesis.
But it is assuming that you know these OP coefficients on the left-hand side on average.
Sums of squares, yeah.
Yeah, sorry, you know the things on the previous slide.
Yeah, that's right. Yeah, that's your input. And from that you expect these functions, yeah. Yeah, and these will be approximate because you compute those. The philosophy would be to compute those semi-classically, so it's in some it's approximate, but it's a good approximation, and that reproduces these answers. Yeah, that's right. Let me skip. Just say that you can you can do more complicated computations. I want to show. This is not going in the right direction. Yes, good. You can do more complicated computations. Let me just skip all of that. You can just do more complicated computations and also get, by looking at higher order correlators, you get higher order terms in your matrix model. So you can do all kinds of other fun computations and see how they scale with entropy. And for example, this would give rise to a quartic term in your matrix model. This would give rise to some quartic term and etc. You can even go to higher order. These things give rise to kth order terms in your matrix model. Well, transfer model, street, etc. So, but that's just, you just do the computations that you feel you can do, you stick them in and you get an improved statistical model with higher order interaction. Yeah, so the final model that you get a statistical model. You can write a generating function for that statistical model, which the sketch of that is this. And that means that these correlators of these C's, they will just be given by varying this generating function with respect to Z. It's all matrix models done. Now, a really interesting question, we skip that one, is the following. Now, suppose that we do lots and lots of semi-classical gravitational computations. When you have one boundary, then you build, based on all those computations, you build the recipe that I gave you, you build a statistical model, which is the best possible description of the theory based on the computations that you did in the one-sided case. So that gives you some matrix model, tensor model, some statistical thing. You can now use that statistical thing to compute correlations between situations where you have two boundaries or three boundaries. And, but you can also try to do gravitational computations when you have more than one boundary. And then the question is, do those gravitational computations with more than one boundary, do they give you new information about the system? Or do they simply reproduce the answers that the statistical one-sided model gives to you? And it appears to be true that wormholes do not give you any new information. So all these gravitational wormhole computations, they simply seem to agree with results that you obtain by first doing one-sided computations, building a statistical model, taking that at face value, and using that to compute multi-boundary correlates.
They just compute mistake.
Sorry?
They just compute mistake.
They just tell you that you found the right statistic. It's kind of fun because you built a statistical model of the semi-classical theory, and you don't know exactly in what cases it applies and in which ones it does not. But then you discover it actually also captures these wormhole solutions of the semi-classical theory. And those in some sense measure mistakes that the model makes. It gives you correlations that are fake. But that are, no, that's right. Yeah, they measure your sort of your ignorance. Yeah.
This is really not. I mean, suppose that you get a different result from the wormhole. I mean, what would you have concluded?
Well, it's a win-win type of situation, right? Because then you would just improve the matrix model, and then so typically what you would then get is in matrix model languages multi-trace deformations of the matrix model. You would have to include those, and then it would be genuinely new information in the wormholes. That's also a logical possibility, but that does not seem to happen.
Or it could be that there is no factorization in the first place. I mean, you could also.
That's right. But all these computations are a bit like factorization agnostic, and because we only do semi-classical computations, so and the semi-classical theory cannot distinguish coarse graining from non-coarse graining. If you do one-sided computations, you just can't.
Is the statistical model you get independent of what you choose to be the fundamental variable? Like instead of a P coefficient, you could parameterize the theory in some different way. And
that's right. Yeah, it's conceivable that if you use different variables, you get something slightly different. You can also ask whether, if you choose other information theoretic measures, whether you get something different. Why is Shannon entropy the preferred measure to use? I don't have a very good answer to either of those questions. You would believe there should be some sort of reparameterization invariance under a choice of variables, but I don't know exactly now how that would be implemented in these types of computations.
Is there a difference in whether you can use more or less information? Like suppose that you add some computations that you can do in gravity and you add it to your procedure to get a different more precise.
Yeah. The model depends on how you decide to what you decide to put in and with what. If you put more and more in, you get a more refined theory. You could also just say, you just do very simple computations that are sitting only in the JT sector of the theory, coming back to your question. Then maybe, you did get a JT matrix model, because that captures precisely those computations. That would be a very bad approximation to the theory, but for those computations, it's precisely the right description.
And which approximation does the wormhole capture? I mean, if you have different possibilities.
Yeah, so I think these, for example, these wormholes so an example where we can do many computations explicitly is in 2D CFTs. And then just doing OPE coefficients at this Gaussian approximation level is enough to capture a large number. That theory contains a large number of wormholes, and those wormholes also agree all with semi-classical computations. So already at a quadratic level, you can see that. Let me quickly show one example, just to give you an idea. So the C's, I did one-sided computations. I got a quadratic tensor model for the C's, just quadratic. So these are Gaussian random variables with some weights. Now, this is the genus 2 partition function. And it contains,
you have always only one AB operator, and delta is the dimension of that.
No, sorry, this is sketchy. These are 3 heavy operators. So this is in some sense, but what should be written here is minus beta delta I, minus beta delta J, minus beta delta K. But if these 3 betas are roughly the same, then this is dominated by the regime where the 3 weights are roughly the same. So this is not an approximation, but yeah, you should write something more complicated in print. So these are all heavy. It's a simple quadratic theory, so you can use Wick's rule to do sort of Feynman diagrams. It's just a quadratic variable. It's a free variable. There are 2 Wick contractions at this Gaussian level. The first one is like this. That just corresponds to the disconnected situation, as you can sort of see from the picture. But then at the Gaussian level already, there's also these connected correlators. And this connected correlator, you can do this computation. You can do a more precise computation than this cartoon here. And you can see that it agrees with this wormhole. So this is the Maldacena-Maus wormhole from 2004. It's just a genus 2 Riemann surface with a simple warp factor. So here you can see that, first of all, that this statistical model does give you these connected correlators. But this is also an example where you get no new information from the gravitational computation because it simply agrees with the prediction that you made.
Yeah, question time. So you can.
I'm in question time, yes. So, great, yeah, there were many questions. Let me just make a few comments and wrap up. No, I'll make a few. That's right, yeah. So you can also predict wormholes. That's also fun. There's still some open predictions for wormholes that have not been found, but their non-existence has also not been proven. So there's just some conjecture that certain wormholes need to exist that are interesting. I should also point out that in this paper, these authors did many more detailed computations using this Gaussian approximation. Their philosophy was slightly different, but the technical computations were literally of this type. And they verified a large number of 3D gravitational computations against this Gaussian approximation and showed that there's a pretty good agreement. Well, it's perfect agreement whenever you can do both computations. No. Yeah. Then I wanted to briefly mention that so one interpretation of these statistical models is that they are some approximation to a UV complete CFT, and they are just a technical way to implement our lack of knowledge of the UV of the theory. You can also take these models at face value and say, well, here I have an interesting representation of a semi-classical gravitation theory. So maybe my matrix/tensor model, maybe it's an interesting thing in its own right. Maybe it's an interesting representation, or maybe it's even a combinatorial representation of semi-classical gravity. And in the 3-dimensional case, you can sort of try to push this a bit more, which is a work in progress. And what seems to come out of that is some weird model. It's quartic. It involves an integral over OPE coefficients and over conformal dimensions. And then there is a bunch of functions in it that basically, what do these functions do? Basically, these functions, they input that modular invariance should be approximately true and crossing should be approximately true. And by approximately true, I don't mean that it holds on average, but also that the variance is small. Otherwise, it could be a very widely spread out thing. And if you want to restrict the variance in crossing, you need to basically add crossing squared as an observable in your theory. And if you add crossing squared, you get quartic terms for OPE coefficients in your tensor description. So you get some sort of model, and it's kind of suggestive because these things are quite complicated, and some of these things involve the 6J symbols of the Virasoro algebra, which are also kind of the same as the 6J symbols of Q deformations of SL2, and so there's a long story, but all these things have been used in the past to build topological 3D quantum field theories. So it's conceivable, although we are very far from proving anything, that this is a nice combinatorial representation of 3D geometry. It would be a 3D version of the old duality between 2D matrix models and triangulations of Riemann surfaces, and the old 2D gravity story from several decades ago.
Why you stop at quartic or you go up?
Yeah, because there's not much to be gained. If you could try to go to higher order, but I don't think you gain much. I don't fundamentally. You could try to add those higher order terms, but somehow. If you want to have a model which in some sense has a notion of bulk locality in it, and that's the most important feature to implement, then to implement that somehow crossing seems to be sufficient. So this might still not be an exact description of 3D geometry, but this is the leading order term that you need to get sort of bulk locality on board, and maybe it's enough to get some sort of 3D. So it's conceivable that this thing is maybe a 3D theory with small higher derivative interactions. So it is not literally 3D geometry, and that you could maybe fix those corrections by some higher order terms. But it should be close to being some sort of combinatorial representation of 3D geometries. But for that, if you don't have this, I don't think you have any notion of locality in the bulk. And if you want to have some notion of locality in the bulk, that's the first. That's really a qualitative thing that requires that. And I think the rest is just small technical improvements that don't buy much. I don't fully understand what exactly these high order terms do.
But this special model is only.
This model is only quartic because the only thing we input, like in a 2D CFT, you know that if you impose crossing and modular invariance of 0 and 1 point functions, that's by more Seiberg and so on, that generalizes the modular invariance at all genus and all insertions. So those are the things that we put in here. And that's supposed to generate, that's supposed to guarantee modular invariance for the full theory.
I meant this.
Oh, well, that's not as complicated as this, because some of these things are not part of this. But especially this fourth order thing has some flavor of this, because the fourth order thing involves 4 C's and some 6J symbol, and those are also the building blocks of this to write your description of 3D DQFT somehow.
So going back to your previous one, the philosophy sort of like is just to create more cyber, where we're saying, suppose we insist that 4-point crossing is approximately a bill, then let us.
That's right.
Imagine that the higher point crossings are all approximately a bill.
Yeah. That's exactly. So it's like a statistical version of more sided. Right.
What is the approximate? The word approximate question. When you say that crossing is approximately a day, what does that mean?
that means it's obeyed up to errors that go like -c or so. Because we cannot exactly solve crossing. And that really is the bootstrap program and so that would require you to have exact 2D CFTs. But you can impose crossing up to exponentially small corrections. That, for example, means that
So this model produces some spectral density and some of the coefficients that will solve crossing them on all genus surfaces.
to exponential accuracy, right? Yeah, which you might think is enough for a semi-classical description because those are the non-perturbative corrections of the theory. That's right. Let me just take the opportunity to say that there's a slightly different perspective that if you want to know more about, you go to Diego's talk in a few weeks, where we try to model everything in terms of averages of states rather than in terms of averages of matrix elements, where you sort of put some of the statistics in the state of the theory. That gives rise to an interesting and rich structure. And that maybe is a bit of an alternative perspective on some of these things, and you can use this alternative perspective to also explain certain wormholes and so on. And that might, maybe ultimately, maybe we need to combine all these ingredients. That's still a bit unclear. This I already discussed. So, just to emphasize again, we built a statistical model based on one-sided computations. We use it to predict wormholes. So far, everything that we seem to get is consistent with the statement that there's no new information in wormholes whatsoever. They're just giving you the correlations that your maximal ignorance statistical model had. It's still a bit unclear whether this is the endpoint, or whether we should build a more involved statistical model, or whether we should use different information measures and so on. So still a bit unclear whether this is what the actual principle is that guarantees that this is the right way to do it. All of this, none of this really, strictly speaking, assumes that the theory is chaotic, because we just put in low energy information. And if the UV theory is not chaotic, it would not affect anything per se. But presumably that would show up at some point in your computation. But this formalism just incomplete information, and that's all that happens. Well, it's also interesting whether if you take this thinking seriously and you apply it, say, to other interesting quantum gravitational examples where we know less, like flat space or de Sitter, and you just take your semi-classical computations that you can do, which maybe in de Sitter is even more straightforward than in flat space. What would be the model that you would get? Like in de Sitter, for example, you could put in that the Hilbert space is finite dimensional because the cosmological horizon is finite entropy. You could put in some knowledge of black holes, try to build a statistical model of de Sitter and see how far you get. So that would be a fun thing to do. The other, slightly annoying lesson for me from all of this is that, unfortunately, not just this, is that, somehow semi-classical gravity is a very strange theory. It seems to be on the edge of allowed theories. And it has been optimized to hide quantum physics from us. You cannot write a theory that is better at hiding quantum physics from us than GR somehow. It has been optimized for that purpose, it seems. It's a bit annoying from like an observational point of view, but that seems to come out of some of these considerations. But maybe in de Sitter and so on, maybe there's more hope.
Again, isn't the fact that gravity actually computes similar things? It seems like this logic applies to some topological sector of gravity, where you have to consider all the different wormhole type solutions. But as I pointed out, gravity, it does compute the correct entropy. Right? This is not an inference. So it knows a bit more than what you're making out, right?
It knows more.
So isn't that the reason to be a bit more optimistic? Maybe not that much more. But,
I'm always optimistic, so that's good. But, this has more to do with things like for example, if you think about the way information comes out, that could not have been coming out of a black hole in a more complicated way as far as low energy observers go than it does. So that's one place where it seems super difficult to detect the quantum nature of gravity. No, it's true. Like the fact that we can do these black hole computations and find the spectral density at high energies, and so that definitely is interesting to the gravity issue. That's for sure. There's something quantum in it because that's finite. That was it. Thanks.
Okay, so we already have a few questions, but maybe we a couple of questions. Yeah, but yeah,
The story you are advocating is talk about the story of the error correcting the correction code.
Story of
Error correcting code is the other. The classical gravity captures the subspace of the Poynting space.
I don't think it's inconsistent. The perspective is different. I think the result is consistent with an error correction perspective. Maybe there's even some sort of statistical physics type of way to derive error correction by inputting the apparent inconsistency of some computations. And the apparent, the breakdown of locality of exact bulk operators. If you somehow put that in some framework like this, I would not be surprised if some of these things like error correction and also, for example, the use of these non-isometric codes that people have used to describe black hole interiors, if that's not something that could in principle be obtained from this.
I think it has been, because there was a recent paper by Farman and his student Chandra, where they, using the Virasoro image, they reproduce random tensor network and they reproduce this isometric to non-isometric transition.
Right, they give an example of precisely this behavior. Yeah. In some sense, these non-isometric things, they're the most chaotic thing that you can write down that sort of maintains low energy physics. So it definitely has a statistical value too. That's right. Yeah.
so.
Sorry, what's your take then on wormhole that we can construct in ADC? Kind of, would you say that based on the fact that wormhole doesn't appear to produce new information, will not be unstable?
Well, this has to do with this UV completion question, and my suspicion would be that in the full UV theory they're all stable. Yeah. But that's my list. I don't have to do it. Again, the two logical possibilities, if you want to restore factorization, were one, they're unstable, and they should not be taken seriously as a saddle, or they are there, but there's lots of other small, stringy, fluctuating things, and if you include those as well, then somehow factorization gets restored. And people have tried to come up with things like that, with exotic ingredients, have wormholes and so on, and suitable sums over into the world range and all that. So maybe that's true as well, but that seems a much more contrived mechanism than simply stabilizing it. But yeah, I think we have verdict to fill out.
Okay, last quick question.
So the fact that these wormholes get reproduced by statistical model, am I right in understanding that now this is like an empirical observation? You just observe in
That's right.
many examples. But could there be a more general argument for this?
No, that would be very interesting, but I don't know what it would look like.
It's really a statement about PR, right?
If you believe that the model that you make, like in the studio example, is some sort of combinatorial representation of geometry in the bulk, then this combinatorial representation should also be applicable to any geometry that you can make, including ones with multiple boundaries. That would kind of explain why the wormhole would be part of it. It should be something in that direction, but I don't have a better explanation.
Okay. So then next time, Jan again.